I'm going to start this topic by looking at exothermic and endothermic reactions, because I want you to think about reactions and think, why do they occur? What makes them occur? Because most of them don't happen spontaneously. That means they don't just happen by themselves. We have to actually do something to them to make them react. So let's have a look at this lump of limestone rock then. That will do nothing unless we heat it up. It will always stay limestone rock and nothing will happen to it unless we heat it up. Same as the methane. Methane will stay methane unless we give it a spark and some oxygen, and then it will burn and then make carbon dioxide and water. Now, as you know, the reaction between methane and oxygen to make carbon dioxide and water is an exothermic reaction. And that is the case for all fuels. There's no point in a fuel making us cold. We want fuels to make us nice and hot. So they're all exothermic reactions. And so these can be represented with an entropy level diagram, which you've done at GCSE. So here I've just done a rough drawing of one, so you can see that the products are lower in energy than the reactants. So we say that the products are more energetically stable than the reactants. And here you can see that the activation energy was provided by usually with the lit splint. Otherwise, if we didn't have an activation energy, all the methane on the planet would spontaneously combust and we wouldn't have any methane. So we have to have a little bit of spark in order to break the bonds in the methane and the oxygen in order for it to react. So this is not a spontaneous reaction. It doesn't happen on its own. It needs a spark to ignite the methane and oxygen, and then we'll make carbon dioxide and water. So this is nothing new. You've learnt this at GCSE. The new word here is this word spontaneous. This reaction is not spontaneous. It doesn't happen by itself. And you can see here this is an exothermic reaction. Delta H is negative. So we have the entropy arrow going down, indicating a negative exothermic reaction. Now let's look at the limestone. Like I said, limestone will not thermally decompose on its own. It needs actually, obviously the hint is in the name, it needs thermal heat. It needs heat in order to decompose. So when we do that, when we heat it up, we make calcium oxide, which we use to make cement and other products, and carbon dioxide is released as a gas. Now, this will not happen spontaneously. We need to put heat energy in. And so you can see here our delta H this time is actually positive because we need to put in energy because it is an endothermic reaction. Again, it's not spontaneous. This is the activation energy. Here it goes from the reactants right the way up to the top of this activation energy hump. So this is the activation energy, and that reaction will not proceed until we give it energy. In the case of heating up the limestone, the calcium carbonate, the calcium oxide and carbon dioxide, which are the products, they're actually energetically less stable than the reactants. So what's actually driving this reaction? Why does this reaction actually happen? So what are spontaneous reactions then, and why do they occur? Let's look at nitrogen dioxide, NO2, and it's a gas, and if we put some NO2 in a sealed container, after a little while, if we have a look at what is the composition mixture, we'll realise that actually we haven't got NO2 anymore. Some of it has actually made N2O4. The reaction is spontaneous and readily reversible, and we get an equilibrium mixture. Again, this has been covered at GCSE and AS chemistry. The forward reaction that makes the N2O4 gas is exothermic. However, the backward reaction is endothermic. This is all spontaneous at room temperature. The position of equilibrium can be reached from either direction. So we could actually put some N2O4 in a sealed container at room temperature, and it will spontaneously decompose to form NO2. Well, some of it will anyway. So this N2O4 making NO2, this endothermic reaction is happening at room temperature without us doing anything to it. We're not heating it up. It is happening spontaneously without us doing anything to it. So what's the driving force then for this reaction to happen? Because it can't be the formation of a more energetically favourable, lower energy products, because the products are higher in energy. So something else must be at play here. And this factor is a quantity known as entropy, which is governed by the second law of thermodynamics, for those of you who are studying physics. You don't need to worry too much about the second law of thermodynamics, because that's all taken care of mathematically in the equations I'm going to go through later. One of my favourite all-time spontaneous endothermic reactions is the reaction between barium hydroxide and ammonium chloride. You may have seen this demoed in the lab. If you haven't, I've provided a link to to an experiment, but there's loads of people that have uploaded it onto YouTube. So take a look, it is amazing. This reaction is very, very unusual because we've got two solids reacting together in the solid state. And it's an extreme endothermic reaction. So it is taking in heat spontaneously without us doing anything to it. We're not heating it up. The heat is provided by the surroundings. And the temperature of this reaction, I think I've got it down to about -23. I don't think it goes colder than that. Yeah, so -23 from a spontaneous reaction at room temperature. So the second law of thermodynamics actually allows us to predict whether a process is likely to occur. So we can look at the second law of thermodynamics to work out and understand what drives chemical reactions forward, and also what determines the position of the equilibrium. Because as we know from our GCSE and AS chemistry, the position of the equilibrium is really, really important if we want to make the reaction proceed more to the product side, so that we have more of a yield. The second law of thermodynamics introduces a term then called entropy. This is a property just like matter or like density or energy, and the simplest way to describe it is it determines how random or disordered a system or a particle is. So entropy is not just about the distribution of energy of the system, it's also the distribution of the molecules and the way they're arranged in space. And it's quite a difficult concept to understand, and I'm not going to go through all the details of entropy in great detail here, because it's not required for A-level chemistry. If you've ever scattered a pack of cards, playing cards, and thrown them up in the air, you will know that they don't ever land one on top of each other in a nice, neat pile. That is chaos theory and disorder. So there is a probability that they could, if you threw them up in the air, that they could, there is a probability they could actually all land one on top of each other in a nice, neat pile. But that's not how our universe works. Our universe is tending towards chaos and disorder. In order to understand entropy, let's look at a very simple molecule. Let's look at water. Entropy has a symbol of S, and its units are joules per Kelvin per mole. Now, it's really important you recognise this is in joules. Most of the time, any data we give you is in kilojoules per mole. When we start putting entropy into equations, we have to allow for this, the fact that it's joules, and everything else, like enthalpy here, is is in kilojoules per mole. So we'll deal with that later on in the video. So let's have a look at the entropy values for water. These are all available in data books. So look at the entropy for gaseous water then, 189 compared to liquid water, which is 48. If we think about it, that's obvious. There are more ways that water molecules in their gaseous state can orientate themselves around in space because they're free to move anywhere. So if you can imagine a water molecule spinning around, it has an infinite number of ways in which it can actually place itself in space and be free to do whatever it likes. So the entropy of steam is 189. And look at, if you look at liquid water, then it's got an entropy of 70. But ice, because the ice crystals, the water molecules are fixed in a lattice, it's got much less entropy. It's much more ordered. It's in a fixed lattice position. So there's less disorder in ice molecules, and gaseous water molecules are much more disordered. With liquid water obviously being somewhere in between, because of hydrogen bonding, we have got a bit more order with liquid water, because the water molecules have less chaos, because they're actually in a liquid, they're hydrogen bonded together, they can't escape the container like the gaseous molecules. So therefore, liquid water is much more ordered than gaseous steam, which is much more disordered. So let's have a look at the reaction between barium hydroxide and ammonium chloride then. We can see here we have solid, solid going to gas, liquid and solid. So the reactant side is more ordered because they are solid. The product side is more disordered because we are making a gas, a liquid and a solid. So the driving force for this reaction, so don't forget this is an endothermic reaction, is actually entropy. Look, we've got 1 mole of barium hydroxide and we've got 2 moles of ammonium chloride. We're making 2 moles of gas from 3 moles of solid, 10 moles of liquid and 1 mole of barium chloride. Don't forget this is water of crystallization, so this is 1 molecule here. So 3 moles going to make 10, 11, 12, 13 moles. We are becoming so much more disordered as this reaction proceeds, especially as we're making gaseous molecules and liquid molecules from solid molecules. So here we can say that this spontaneous endothermic reaction is driven by entropy as the system is becoming more disordered. The particles are more random and the distribution of the energy between the particles is becoming more random. Even without the entropy values for this reaction, we can predict that entropy will be increasing because we have 3 moles of solid on the reactant side, and we've got 10, 12, 13 moles of products. So, and 2 moles are gas and 10 moles are liquid. So the system is becoming more disordered. We have gaseous molecules being formed and liquid molecules being formed from solid. So we know that entropy is going to be increasing. So how do we calculate entropy then? Well, basically we go and look at for the molecules and our reactants and our products in data tables, and look for the entropy values that have already been calculated. And you can see I've put these in here. Barium hydroxide, because it's got 8 waters of crystallization, it's actually got quite a high entropy. It's quite unusual for a solid. Ammonium chloride, that's a bit more of a usual entropy value for a solid, 95 there, look. Ammonia as a gas is higher in entropy than the solid, 192. We would expect that because gaseous molecules are more chaotic and more disordered. There are more arrangements of them in space. They can rotate. They don't have as many interactions between other molecules. So energy is much more dispersed. 10 moles of liquid water, look, water has an entropy of 70 when it's in the liquid state, and then barium chloride in the solid state, entropy of 124. Don't get too caught up on the numbers because they're always given to you in the exam, and you don't need to know why one is higher than the other. That's way beyond the specification. So how do we work out total entropy, the entropy change then? It's the sum of the entropy of the products take away the sum of the entropy of the reactants. So without even putting these numbers in, we already know that it's going to be a positive number because we already know that entropy is increasing. So now we can put the numbers in. And you can see here I've done the calculation. We've got 2 moles of ammonia, so 2 times 192. Really importantly doing this calculation, look at the stoichiometry. 10 moles of water, so 10 times 70. We've only got 1 mole of barium chloride. And then be careful with your calculator. Make sure you use your brackets properly, because then you've got to take away the 427 from the barium hydroxide, which has got 8 waters of crystallization in 1 mole. But it's just 1 mole of it, look, so it's just 427, and then 2 times 95 because we've got 2 moles of ammonium chloride. And if you do that correctly, you should get a value for the entropy for this reaction is plus 591. That is a huge value. So that is the driving force for this reaction happening spontaneously at room temperature. And it's an endothermic reaction. Is actually happening at room temperature, is taking in so much energy from the surroundings in order to make that reaction proceed without you doing anything to it. And the reaction will get so cold that it will go down to minus 23 just from the room temperature conditions. Okay, so let's just check your understanding then. Let's have a think about whether we can predict whether some of these reactions are going to have an increase in entropy or a decrease in entropy. So hydrogen chloride gas reacting with ammonia gas. Again, you might have seen this in the lab. You get misty white fumes of ammonium chloride solid being formed. So has the system become more ordered or more disordered? Has entropy increased or decreased? If we're going from, we've got 2 moles of gas going to 1 mole of solid, then the system is becoming more ordered. So hopefully you should have realised that as we're becoming more ordered, as 2 moles of gas are making 1 mole of solid, therefore entropy is decreasing because the system is becoming more ordered. In exam questions, you'll be expected to explain why. You can't just put there's been a decrease in entropy. You have to say why. You have to talk about the states of the products and the reactants, and mention the fact that gas is more disordered than a solid. Let's have a look at hydrated copper sulfate then. You've probably been doing this reaction for many years. So it's lovely blue crystals. And when you heat them up, you get white anhydrous copper sulfate, and you should see water condensing on the side of the test tube. This is obviously a reversible reaction. It's endothermic in the forward direction. We have to put heat energy in order to decompose the hydrated copper sulfate. And then if we put the water back into the anhydrous copper sulfate, it releases the same amount of heat energy that was taken in to drive the forward reaction. So this is a reversible reaction, but this time we're just looking at the entropy. So how we've got 1 mole of hydrated copper sulfate salt going to make 1 mole of anhydrous and 5 moles of water. So is the entropy going to increase, decrease, or stay the same? In this case, it's becoming more disordered. So entropy increases. So on the left-hand side, on the reactants, we've got 1 mole of solid going to make 1 mole of solid product and 5 moles of liquid product. So therefore, we're becoming much more disordered, so entropy increases. For the last example, let's consider the Haber process then. We have 1 mole of nitrogen, 3 moles of hydrogen, making 2 moles of ammonia, all in their gaseous state. Is the forward reaction going to have an increase, a decrease, or no change in the entropy of the system? When we were looking at equilibria at GCSE and AS chemistry, you were making predictions on the positions of equilibrium, and here we've got 4 moles of gas going to 2 moles of gas. So we are becoming more ordered. So therefore, entropy will decrease in the forward reaction. What does this mean? Well, it means that it's very unlikely that nitrogen and hydrogen will make ammonia spontaneously. However, if we look at the reverse reaction, where ammonia is making nitrogen and hydrogen, you can see that 2 moles of gas is going to make 4 moles of gas. So therefore, entropy is increasing. The system is becoming more disordered. It's important that you realise that it's not just entropy that decides whether a reaction is feasible or not. And Josiah Gibbs actually found a mathematical relationship that linked entropy and enthalpy in his equation. His equation, delta G equals delta H minus T delta S, combines both enthalpy and entropy in a system along with temperature. Now, some reactions are not feasible unless the temperature is changed, and this is very, very important for industrial chemists. So with delta H values, the enthalpy values of a reaction, and the entropy values of a reaction, we can adjust the temperature to make the reaction feasible. This amazing equation allows industrial chemists to try and lower temperature of reactions so that we use less energy. Maybe we might use a better catalyst. So all these things all come into play when we're trying to work out a reaction and trying to get it to actually work at as low a temperature as possible. We do have to look at the enthalpy of the reaction. Is it exothermic or endothermic? And is the system becoming more ordered or more disordered? And those two thermodynamic factors, delta H and delta S, are brought together in this equation. I'm not going to go into that in any detail. That's going to be covered in another video. So that concludes this video. Hopefully this helps. Thank you very much for watching.